Right. Class 80, we are going to start using Snell's law to predict, angles of incidence, angles of refraction, and indices of refraction. Basically, Snell's law is an equation we use to calculate and predict how at what angles will light refract. All right, or to use the refraction to predict the indices of refraction. So what we're looking at in this image here, on the left-hand side is material 1. On the right-hand side is material 2. On the left-hand side, it has an index of refraction of 1. On the right-hand side, it has an index of refraction. It should be not of 1, but n equals 1. On the right-hand side, the index of refraction is given by n2. The angle of incidence we measured in class is 34 degrees. That's measured with respect to the normal line. The angle of refraction, theta 2, is 18 degrees. Again, we measured that in class using a protractor. So make sure you're able to measure those two fairly accurately. So Snell's law is given to us as n1 sine theta 1 equals n2 sine theta 2. So we're going to find the index of refraction of material 2 here. We're going to assume that material 1 is air. So n1 equals 1, right, because it's air. N2 is our unknown. Theta 1, theta 2, let me just double check what those are again, 34 and 18. So we have n1 sine theta 1 equals n2 sine theta 2. So we have 1 sine 34 equals n2 sine 18. All right, looking at these, just make sure you have the degree symbol on your angles here because that is a unit. Just don't forget to make sure your calculator's in degrees mode. Very important. All right, so work through the calculations here. I'm not going to show every step, but you should end up getting n2 equals 1.81. Actually, you know what? I will show a few more steps there. So let's do 1 times the sine of 34. This is 0.560 equals n2, and then the sine of 18 is going to be 0.309. Divide both sides by that number. .560 divided by 0.309, we get about 1.81. Then we use a simulation here, and one thing we found, and this is an important concept. When light goes from a higher index of refraction to a lower one, it bends away from the normal. When it goes from a lower index of refraction to a higher one, it bends toward the normal. So another way of saying this is if n1 is greater than n2, theta 2 is greater than theta 1, and vice versa. Okay, what do we mean by this toward or away from the normal? Well, let's look at a low to high. Let's look at the one we just did. So this is going from an index of refraction of 1, which is air, to an index of refraction of 1.8, which is on the right. When the material was when the light was in air, it was 34 degrees away from the normal. When it makes it into material 2, it's only 18 degrees away from the normal. It got closer. We say it bent toward the normal. All right, so that's what we mean by that. All right, looking at number 4 here, it says, a ray of light travels through a mineral submerged in water. Which material has a greater index of refraction, the mineral or the water? Explain. So let's see what we have here. Theta 1 is given to us here, okay? That is 27 degrees because it's always the angle with respect to the normal. Theta 2 is 41. Okay, so what we can establish is that theta 2 is greater than theta 1. That means that n1 is greater than n2. Okay, it's kind of like the opposite. I wouldn't say inverse, but it's kind of the opposite. Okay, so the mineral must have a greater index of refraction than the water. Okay, because the light bent away from the normal. It was 27 degrees away from the normal. Now it's 41 degrees away from the normal. So the light bent away from the normal. Therefore, it is a high n to low n problem. The higher n is first, n1. The lower n is second, n2. All right, let's do a couple Snell's law questions. The light travels from zircon, which has an index of 1.92, into corn oil. So that's N2. We always go into N2. So that's 1.47. Okay, make sure you can find that on your chart. If you don't know where the chart is, look at the previous class. The light in zircon contacts the boundary at an angle of 20 degrees. That's theta 1. So as the light enters the cornoil, it will bend. Will it bend toward or away from the normal? Well, this is a high to low question, so it will bend away from the normal. Okay, that means that theta 2 is greater than theta 1 because n1 is greater than n2. All right. So here's a little picture of what's going on here. I drew it on the right-hand side here. All right, so let's do Snell's law and figure out what this angle is. So we have n1 sine theta 1 equals n2 sine theta 2. N1 is 1.92 sine of theta 1 is going to be 20 degrees. N2 is going to be 1.47 sine theta 2. 1.92 sine of 20. We have 0.657 equals 1.47 sine of theta 2. We're going to divide that by 1.47. We have 0.447 equals sine theta 2. And here you have to do the inverse sine to get rid of that, to get theta 2 alone. So sine to the negative 1 is 0.447 equals theta 2. It's about 26.6, 26.5. Yes, this agrees with our prediction. Theta 2 was greater than theta 1. So now we're going, okay, actually here it gives us the refracted angle. We're going from air into quartz, so that's N1 and that's N2. We're always going into N2. Again, find the index of refraction of quartz on your reference table. And theta 2 is going to be 43 degrees because that's the angle it refracts at. So is the angle of incidence greater than or less than the angle of refraction? Okay, well, let's see. We're going from low to high. So the light is going to get closer to the normal, which means 43 is closer to the normal than theta 1, the angle of incidence. So since N2 is greater than N1, theta 1 must be greater than theta 2. All right, let's do Snell's law and check this one out, confirm it. By the way, our givens are all listed up here. I'm just doing a video real quick. So we have N2 is 1.46, and we have the sine of 43 degrees is our refracted angle. So let's bring that down. So we have sine of theta 1 equals, so throw in your calculator, 1.46 times the sine of 43 degrees. We should get 0. And don't round this one, 0.996. To get theta alone, you have to do the inverse sine of both sides. So theta 1 equals the inverse sine of 0.996. And that should come out to be about 84.7 degrees. So does this agree with our prediction? Well, theta 1 is 84.7 and theta 2 is going to be, looks like it was 43 degrees. So yeah, theta 1 is greater than theta 2. So it does confirm our prediction.